All right, strap in everyone, because today we're going deep into the quantum realm. We're going to explore the really mind-bending world of information physics. You want to know how information and physics are all mixed up together? And we're using Leonard Susskind and Art Friedman's book as our guide, Quantum Mechanics, The Theoretical Minimum.
Oh, that's a good one.
Yeah, specifically we're looking at lectures 1 through 4, 7 through 10, and the appendix. So get ready for a wild ride through quantum states, uncertainty, entanglement, and the strange link between particles and waves.
You know, it's really fascinating how information physics challenges how we usually think about how the world works. It's like, suddenly we find out the universe has a whole other rule book than we thought.
But like gravity's just a suggestion.
Hmm.
The book really hits hard on this point that quantum mechanics is just fundamentally different from classical physics. They use this analogy of a spinning coin. And I thought that was really helpful to kind of illustrate this.
Yeah, the spin example. I mean, it's a classic for a reason. It really highlights the difference between how classical and quantum systems behave. Like, in classical physics, you can measure a system, like figure out which way a coin landed, and that's it, right? But in the quantum world, the actual act of measuring can change the system itself.
So it's not just about observing the coin. It's about the observation changing the outcome. Whoa, okay, that's already bending my brain a little bit.
Yeah.
And then the book talks about this concept of a qubit,
Right.
like a quantum bit.
Exactly. So a qubit is like the quantum version of a classical bit. And the amazing thing is a qubit can be in a superposition, meaning it can be like a blend of states 0 and 1 at the same time. And it's only when you measure it that it collapses into a definite 0 or 1.
So it's like a coin spinning in the air, both heads and tails, until it lands. And the landing is the measurement. And what I thought was cool is the book explains this with state vectors.
Yes.
It's like a math way to describe this whole quantum state situation.
Right. State vectors give us like a math framework. But the key is knowing the state vector doesn't mean we know exactly what the outcome will be when we measure something. Instead, it tells us the probabilities of all the possible outcomes.
Okay, so the state vector is like a cheat sheet, but not for the exact answer, just the odds of getting different answers.
Exactly.
That's wild.
Yeah, and going back to the spin thing, the book like visually represents these spin states as vectors in a two-dimensional space. You can picture them as like arrows pointing in different directions, kind of like a compass needle.
Okay, so different directions, different spin states, but the qubit can be a mix of these states, right?
Mhm.
That's where the superposition comes in. It's like the arrows pointing in multiple directions at the same time until we force it to settle on one when we measure it.
You got it. And the book even mentions that the overall phase factor of the state vector, like that can be ignored because it doesn't really impact the physical measurements. It's kind of like a hidden mathematical layer that doesn't affect the observable reality.
Okay, so we've got these quantum states represented by vectors, but then how do we measure things in this crazy world? The book gets into these concepts called observables and operators, and I'll be honest, that's where things started getting a little fuzzy for me.
Well, observables are simply the physical quantities that we can actually measure, like the spin of our coin. And in quantum mechanics, we represent these observables with mathematical objects called operators. And you can kind of think of an operator as a mathematical function that acts on a state vector and extracts information about whatever the observable is.
So if the state vector is our raw ingredients, the operator is like the recipe that tells us how to combine them to make a specific dish, which is like the measurement.
I like that. That's a fantastic analogy. And the book really highlights Hermitian operators as a specific type. They're really important because their eigenvalues, which are like the possible results of a measurement, are always real numbers. And that makes sense because when we measure things in the real world, we get real numbers, right?
Right. Okay, that makes sense. So operators help us pull out information about the system. But we know that these quantum states are constantly evolving, so how does that work? Enter the Schrödinger equation, which honestly sounds pretty intimidating.
Yeah, the Schrödinger equation. It may sound daunting, but it's essentially an equation that governs how quantum states change over time. And guiding this whole evolution is the Hamiltonian, which represents the total energy of the system. So it basically dictates how the system sort of unfolds over time, like a conductor leading an orchestra.
So the Hamiltonian is like the system's instruction manual. It tells us how the energy levels contribute to the behavior and how it evolves.
Precisely. And what's really interesting is that the quantum equation for like the rate of change of momentum closely resembles Newton's equation from classical physics. It's a really cool connection.
Yeah, like finding a familiar landmark in an alien world. Okay, so we've got quantum states changing over time, but then things take an even weirder turn with the Heisenberg uncertainty principle, right? Yeah, I think even people who have never opened a physics book have at least heard of that.
Oh, yeah. The uncertainty principle. It's definitely one of the most, iconic and counterintuitive concepts in quantum mechanics. It basically states that we can't know both the position and the momentum of a particle, perfectly accurately at the same time. So the more precisely we know one, the less we know about the other.
It's like trying to nail down both ends of a slippery rope. As soon as you think you have one end, the other one wiggles free.
Mm.
And the book explains that this arises from the fact that the operators for position and momentum, they don't commute. The order in which we apply these operators actually matters,
Right.
which is so different from how we usually think about math.
Yeah, absolutely. And this non-commutativity, it's a key feature of quantum mechanics. It really underlines how different it is from classical physics.
Okay, so we can't know everything about a quantum system with complete certainty. But even with that limitation, things are about to get even weirder. Because next up, entanglement.
Oh, yeah. Entanglement is where quantum mechanics really starts to mess with your head. It's like two or more quantum systems get linked together in a way that just defies our usual understanding of space and information. Imagine you have two coins. And no matter how far apart they are, if you flip one and it lands on heads, you instantly know the other one landed on tails, even before you look.
Wait, so is it communicating faster than the speed of light? That doesn't seem possible.
That's the crazy thing. It doesn't actually violate the principle of locality. It's not that information is traveling faster than light. It's more like these entangled systems. They share a single state, like a single destiny, even if they're separated by, huge distances.
Okay, I'm trying to wrap my head around that. It still feels spooky, like they have some telepathic connection or something. But how do we even begin to describe these systems mathematically? The book mentions these things called density matrices.
Yeah, density matrices are a really handy tool for dealing with entangled systems. They allow us to focus on a specific subsystem within this larger entangled system without getting, lost in the whole interconnectedness, like having a zoom lens letting you focus on a particular area within a large landscape.
So if we're interested in just one of the coins, we can use a density matrix to zero in on its state without worrying about the other coin across the universe.
Exactly. It helps simplify things, helps us understand what we can observe and measure in a subsystem of this larger entangled system.
All right, we've covered some really mind-bending territory so far. Quantum states, operators, the Schrödinger equation, the uncertainty principle, and now entanglement. I need a moment to catch my breath. But before we do that, there's one more piece of this puzzle we need to tackle. The relationship between particles and waves.
Ah, yes. Wave-particle duality. This is where quantum mechanics really throws our classical intuitions out the window. The book explains how particles, like electrons, can actually exhibit wave-like properties. It's like they have a split personality. Sometimes they act like a little ball of matter, and sometimes they act like a ripple spreading through space.
Wait, so an electron can be both a particle and a wave. How is that even possible? My brain is officially starting to melt.
Well, it's one of the great mysteries of quantum mechanics. The math tells us we can describe a particle's state with a wave function, which essentially maps out the probability of finding the particle at a certain point in space.
So instead of a pinpoint location, we have this wave function that shows us all the possibilities for where the particle might be. It's like a treasure map, but instead of an X marking the spot, there's a whole blurry region where it could be.
Yeah, I like that. And there's another really cool thing. The momentum of a particle is inversely proportional to its wavelength. So a particle with a very short wavelength has very high momentum and vice versa.
Okay, smaller wavelengths, more momentum, interesting connection. But why does that matter?
Well, this relationship between momentum and wavelength actually has huge implications for how we study the microscopic world. So to investigate really tiny objects like atoms, we need to use particles with really high momentum. That's why physicists build these giant particle accelerators, right? To smash particles together at incredible speeds, giving them the momentum to probe the smallest structures of the universe.
So it's like needing a really powerful magnifying glass.
Yeah.
And to get that magnification, you need these huge accelerators.
Exactly.
That's amazing.
It is. And this concept of momentum and wavelength also helps explain how microscopes work. So the resolving power of a microscope, its ability to distinguish between two close objects, it's limited by the wavelength of light that it uses. So the shorter the wavelength, the finer the details you can see.
So the quest to see smaller and smaller things is really a quest for shorter and shorter wavelengths, which then means higher and higher momentum. It's like a never-ending arms race to see what we can observe.
Exactly. It's a constant pursuit of knowledge, driven by this desire to unveil the hidden structure and mysteries of the universe.
Okay, I'm starting to get a little overwhelmed by all this wave-particle duality. But before I totally lose my grip on reality, the next topic is the harmonic oscillator. I remember studying that in physics class, but I have a feeling it's going to be a lot more complex in the quantum realm.
Yeah, the harmonic oscillator might seem like a simple concept, picture a pendulum swinging back and forth, but in quantum mechanics, it's a really fundamental model with a surprising range of applications.
So it's more than just a swinging pendulum. What else can the harmonic oscillator describe?
Oh, it shows up everywhere, from the vibrations of atoms in a molecule to the behavior of electromagnetic waves. It even plays a role in quantum field theory, which is like our current best framework for understanding fundamental particles and forces.
Wow, so it's like the Swiss Army knife of quantum mechanics.
Pretty much.
It's got a tool for everything. So how does the quantum harmonic oscillator differ from the classical one we learned about in high school?
One key difference is that the energy levels of the quantum harmonic oscillator are quantized.
Quantized. You mean they can only take on specific values, like climbing a ladder, where you can only step on the rungs.
Yes, that's a great analogy. And this quantization of energy has really significant consequences for the quantum harmonic oscillator's behavior. Like, it leads to things like zero-point energy, where even at its lowest energy state, it's still got this tiny residual energy.
So even when it's seemingly at rest, there's still this, like, quantum buzz going on.
Exactly.
Wild. But how do we actually figure out the energy levels and states of the quantum harmonic oscillator? The book mentions solving the Schrödinger equation, but I'm still a little traumatized from my last encounter with that.
I hear ya. The math can be a bit much. But fortunately, there's a more elegant way to approach it using these special operators called creation and annihilation operators.
Creation and annihilation operators?
Yeah.
Okay, those sound intense. What do they do?
Well, think of them as like buttons on that energy ladder we were talking about. The creation operator bumps the oscillator up a rung, adding a quantum of energy, and the annihilation operator brings it down a rung, removing a quantum of energy. They're basically mathematical tools that help us navigate those energy levels.
So they're like elevator buttons for the quantum energy ladder. That's much better than wading through all those equations.
Right, and these operators have this beautiful mathematical structure that makes calculating the energy levels and states of the oscillator much easier. It's one of those aha moments in quantum mechanics that really makes you appreciate the elegance of the theory.
I'm starting to see why these creation and annihilation operators are such a big deal. They streamline the math and give us a more intuitive way to understand the quantum harmonic oscillator. Do they have applications beyond this model, though?
Absolutely. They play a crucial role in quantum field theory, which is, like we said, the framework for understanding particles and forces of the universe. So understanding these concepts, operators, and the harmonic oscillator actually lays the groundwork for understanding some of the most fundamental questions in physics.
It's like we're slowly building up this toolkit for exploring the quantum world. Each concept, each equation, each operator is a new tool that lets us go deeper into the mysteries of the universe. But before we get too carried away with our quantum toolkit, I think it's time for a break. We've covered a lot of ground in this first part of our deep dive, and I need a moment to let my brain catch up with all this.
I agree. We've only just scratched the surface of information physics. There's so much more to explore.
All right, we'll be back soon to continue this journey into the strange world of information physics. Stay tuned.
As we go deeper into this quantum world, one of the really remarkable things we find is that the harmonic oscillator, with its quantized energy levels, actually reveals something really fundamental about energy itself. In classical physics, we tend to think of energy as this like smooth, continuous flow. But in the quantum realm, energy comes in these like discrete packets, like little bundles of energy called quanta.
So instead of a steady stream, it's more like energy comes in little bursts or chunks.
Exactly. And these tiny bundles of energy, these quanta, are actually what we call photons. They're the fundamental particles that make up light and all electromagnetic radiation. And the energy of each photon is directly tied to its frequency, which in turn is linked to its wavelength. This relationship, energy, frequency, wavelength, it's like One of the cornerstones of quantum mechanics.
So a three-way connection.
Yeah.
Energy, frequency, wavelengths are all linked at this fundamental level.
Yeah.
Okay, that's pretty mind-blowing. And it all ties back to those quantized energy levels in the harmonic oscillator.
Right. It's like the harmonic oscillator is holding this secret code to understanding energy at the quantum level. And this has huge implications for all sorts of things, from the stability of atoms to how lasers work.
So we've been talking about how quantum mechanics has changed how we think about particles, waves, and now energy. But how does all of this connect back to information physics? We started this deep dive talking about information, but it feels like we've gone pretty far down this physics rabbit hole.
Yeah, we've been exploring a lot of physics concepts. But the really fascinating thing about information physics is that it brings all these ideas back to the concept of information. One of the key insights is that information isn't just some abstract concept, it's deeply connected to the physical world, especially at the quantum level.
So information is more than just bits and bytes stored on a computer. It's somehow woven into the fabric of reality.
That's the idea. And we see hints of this in many of the concepts we've discussed. For example, the state vector of a quantum system. You can think of it as containing all the information about that system. When we make a measurement, we're essentially extracting information from that state vector. But at the same time, we're also changing the state vector itself.
So it's like information is an active participant in the quantum world. It's not just a passive observer. It's actually influencing the systems we're studying.
Exactly. And this realization has opened up all sorts of questions for physicists. Like how information might play a role in things like black hole thermodynamics, and even in the evolution of the universe as a whole. It's a really rapidly developing field that could change our understanding of some of the biggest mysteries in cosmology.
Okay, my mind is officially blown. The universe as a giant information processing system. But if information is so central to the quantum world, how do we even measure it? What are the tools and techniques we can use to try to understand quantum information?
That's a great question. The book spends a lot of time discussing measurement in quantum mechanics. One key point is that any measurement involves both the system we're interested in and the apparatus we use to make the measurement. And here's the crucial part. We have to treat the apparatus itself as a quantum system, subject to the same rules as the system we're measuring.
So the measuring device isn't just a neutral observer. It's entangled in the whole quantum dance.
That's a fantastic way to put it. And this entanglement between the apparatus and the system is really important for understanding how information gets transferred during a measurement. We can look at the final state of the apparatus and deduce something about the initial state of the system we were measuring, even though that system might not be in a definite state anymore after the measurement.
So the apparatus is like a detective, capturing a snapshot of the system's state before it all gets blurry.
Exactly. And this highlights a key difference between classical and quantum measurements. In classical physics, we often assume that we can measure things without disturbing the system too much. But in the quantum world, the act of measurement inevitably changes the system we're looking at.
That makes me wonder about the role of the observer in all of this. Does consciousness, the awareness of the person making the measurement, does that play a role in quantum mechanics?
That is a question that has sparked endless debate among physicists and philosophers. And honestly, there's no definitive answer yet. The book touches on this briefly, mentioning how some physicists have proposed interpretations that involve consciousness. But ultimately, the role of consciousness in quantum measurement remains a mystery.
So the observer is still an enigma, an unknown variable in the equation. But I have a feeling this whole information physics framework is going to have some pretty mind-blowing implications as we continue to explore it.
Oh, definitely will. One of the most fascinating things about information physics is its connection to the very nature of reality itself. If information is so deeply intertwined with the physical world, what does that tell us about what reality actually is?
That's a big question. Are you suggesting that information might be the fundamental building block of the universe? Like instead of atoms or quarks, it's all just bits of information at the most fundamental level?
It's a possibility that some physicists are taking very seriously. The idea is that the universe might be, at its core, made of information, and the laws of physics are just the rules for how this information is processed and transformed.
Wow, that's mind-blowing. It's like saying the universe is a giant computer running some super complex code. But what would that mean for our understanding of things like space and time? Would they still be fundamental in this view?
Those are great questions, and again, they're questions that physicists are still trying to figure out. If the universe is fundamentally made of information, It's possible that space and time might emerge from this information in ways we don't fully understand yet.
So instead of being the stage on which everything happens, space and time might be more like characters in the play, coming from some deeper information structure. It's like those holographic projections where a 3D image pops out of a 2D surface.
Yeah, that's a great analogy. It really captures the essence of the idea. It's definitely a radical concept, but one that's gaining more attention as we learn more about information and its role in the universe.
Okay, I need a moment to process all of that. This whole information physics thing is like falling down a rabbit hole, where everything we thought we knew about reality is upside down. But before my brain totally melts down, let's talk about a specific example from the book that really highlights this connection between information and physics. The qubit.
Ah, yes, qubits,
Right.
the quantum building blocks of information, the quantum counterpart to the bits we use in classical computers.
Right, so classical bit is either a 0 or a 1. But a qubit can be in a superposition of both, right? It's like it can't decide which state it wants to be in.
Exactly. And this ability to be in multiple states at once is what gives qubits so much potential. They can store and process information in ways that classical bits just can't.
Okay, so how do we represent this information in a qubit? I remember the book talking about vectors and matrices, but my linear algebra is a bit rusty.
Don't worry, it's not that complicated. Think of a qubit as an arrow pointing in a certain direction, and we can represent this arrow with a vector, which is just a list of numbers that specify the direction and length of the arrow.
So if the arrow is pointing straight up, that's a qubit in the state 1, and straight down is a qubit in the state 0.
You got it. But here's where it gets interesting. The arrow can also point in other directions, representing a superposition of 0 and 1. So if it's pointing diagonally, the qubit is in a mix of both states.
So the qubit is indecisive until we force it to pick a side when we measure it, like a quantum coin that's both heads and tails until it lands.
Perfect analogy. And this indecisiveness, this ability to be in multiple states at once, is what makes qubits so powerful for computation. It allows them to explore many possibilities at the same time, which could speed up certain calculations exponentially.
Okay, so we have these qubits represented by arrows or vectors. But how do we actually manipulate these qubits to do computations? The book mentions something called quantum gates, which sounds like science fiction.
Quantum gates are the quantum version of logic gates in classical computers. They're operations that transform the state of a qubit, and we can represent them mathematically using matrices.
Matrices, those grids of numbers.
I know, matrices can seem a little intimidating, but think of them as recipes for transforming our qubit vectors. So when we apply a quantum gate, it's like we're mixing up the ingredients of our qubit state according to a specific recipe.
So if we have a qubit pointing diagonally, representing a superposition, we can apply a quantum gate to rotate that arrow to point straight up, collapsing it into the state 1.
Exactly. There are all sorts of quantum gates, each with its own way of transforming the qubit state. Some gates flip the qubit, some rotate it, some even entangle two qubits together.
Entangle two qubits together. Okay, that sounds seriously spooky. How does that even work?
Well, entanglement is definitely one of the most mind-boggling things in quantum mechanics, but it's also one of the most powerful. When two qubits are entangled, they're linked together in a way that just doesn't make sense to us classically. It's like they're two sides of the same coin, no matter how far apart they are. If you flip one, the other one instantly knows which way to land, even if they're light years away.
Whoa, that's crazy. It's like they have this instant telepathic connection.
Yeah. It's not about communication in the usual sense. It's more like they share a single state, a single destiny, even when separated by huge distances. And this shared state allows us to do computations on both qubits at the same time, even when they're physically apart.
Okay, I think I need to lie down. But I'm starting to see how entanglement could be really powerful for quantum computation. It's like having a shortcut that lets us manipulate multiple qubits at once.
Exactly. Entanglement is one of the key things that makes quantum computers so powerful. It allows them to tackle certain types of calculations exponentially faster than classical computers.
So we've got these qubits, these quantum gates, and this spooky entanglement thing. But how do we actually build a quantum computer? What are we talking about physically? Is it all theoretical, or are there real quantum computers out there?
That's a great question, and it's one that scientists and engineers are working hard to answer. There are lots of different ways to try to build quantum computers, each with its own challenges and advantages. Some approaches use trapped ions, where individual atoms are held in a magnetic field and manipulated with lasers. Others use superconducting circuits where tiny loops of wire are cooled down to extremely low temperatures, so they exhibit quantum behavior.
So we're talking about manipulating atoms and circuits at the quantum level.
Yeah, it's incredibly difficult. Building a quantum computer is one of the most challenging technological feats we've ever tried.
So it's safe to say we won't be seeing quantum computers on our desks anytime soon.
Probably not. But the field is moving very quickly. Many experts think we're on the edge of a quantum revolution. In the next few decades, we might see quantum computers changing things like medicine, material science, and AI in ways we can't even imagine yet.
Okay, I'm definitely excited to see what happens with quantum computing. But I think we've covered enough ground in this part of our deep dive. My brain needs some time to process all this.
I agree. We've come a long way through the quantum landscape, from the harmonic oscillator to qubits and entanglement. But the journey's not over yet.
Right, there's still more to explore in this world of information physics. We'll be right back for the last part of our deep dive, so don't go anywhere.
Yeah, it's a really exciting time to be working on quantum computing. While all the experimentalists are busy building these complex machines, theorists are working hard on the algorithms and the applications that'll really make them shine.
Oh, so it's kind of a two-pronged approach.
Yeah,
You need the hardware and the software to make this revolution happen.
exactly. They work together. Theorists need to know what quantum computers can and can't do to design effective algorithms, and the experimentalists need these algorithms to help them build better, more powerful machines.
Okay, so what kind of algorithms are we talking about? What can these quantum computers do that our regular computers can't?
Well, one of the most famous quantum algorithms is Shor's algorithm. It can factor large numbers way faster than any classical algorithm we know of.
Factoring numbers. That sounds like math class, and not in a good way. Why is that such a big deal for quantum computers?
It might sound boring, but factoring big numbers is really important for cryptography. Like, all our online transactions rely on the fact that it's hard for computers to factor big numbers.
Oh, so if quantum computers can factor big numbers quickly, does that mean all our online stuff is at risk?
It's a real possibility, something we need to be careful about. That's why people are working on new encryption methods that can resist quantum attacks. It's like a code-breaking arms race, trying to stay ahead of the quantum hackers.
That's like a spy movie in math. So it's not just about abstract ideas. There are real consequences to all of this quantum stuff.
Absolutely. Quantum computing could have a huge impact on our lives, and not just with cryptography. It could revolutionize things like medicine, materials, and even AI, leading to breakthroughs we can only imagine right now.
That's incredible. It feels like we're on the edge of something totally new, a quantum leap forward. But before we get lost in all the possibilities, I want to step back for a second and talk about the big picture. What are the implications of all this information physics stuff? How is it changing how we think about the universe?
That's a big question. I think it's safe to say we're just starting to understand the full impact of information physics, but one really interesting idea is that information might be more fundamental than we thought.
More fundamental. What does that even mean?
It means information might not just be a way to describe the world, it might be the very foundation of reality. Some physicists believe that at the most basic level, the universe is made of information. The laws of physics would then be rules for how this information is processed.
Whoa, that's like saying the universe is a giant computer running on code we're just starting to figure out. But if information is so basic, what happens to our ideas about space and time? Even consciousness?
Yeah, those are some of the biggest questions out there. And to be honest, we don't have all the answers yet. But information physics gives us whole new ways to think about these things. It's making us rethink our most basic assumptions about reality itself.
So it's not just about building faster computers, it's about figuring out what the universe is really made of.
Exactly.
Wow, that's amazing.
It is. Information physics is a young field, but it's already changing how we think about the universe and our place in it.
It's like we're standing on the edge of a huge, unexplored territory, full of mysteries and possibilities. And the only way to explore it is to keep asking questions, keep pushing the limits of what we know, and embrace the unknown.
I like that. The search for knowledge never really ends, and information physics is like a guiding light, leading us toward a deeper understanding of the universe and how we fit into it all.
Well, my brain is definitely full after all that. We've gone from basic quantum mechanics to the really big ideas of information physics. It's been quite a journey.
It really has. I hope everyone listening is inspired to learn more about this incredible field.
Me too. There's so much out there to discover, so keep exploring and keep those brain cells firing. Until next time.